Good morning, everyone. Welcome to today's lesson. Uh, I think we have a quorum, so we can start. I'll start with if there are any questions. If you looked at the notes, um, and then you have questions, maybe we can spend. If you have any question, you can ask now before we start. Looks like there are no questions. So the last thing we are looking at was the channel capacity of a channel. I mean the channel capacity for different type of channels, and uh, I think we have to look at this the channel capacity or binary symmetric channel. Of course, like all channel, the mutual information, and once you get the mutual information, you have to get the maximum of the mutual information, and that will give you the channel capacity per symbol. And if you know the symbol rate, then you can be able to work out the channel capacity. Um, we are not going to go through this. Actually, this can be derived, and I thought actually the revision of this is going to make part of your assignment. That is just to show that the capacity, the channel capacity of a channel is given by this. Yeah, it is easy to prove. Yes, Samuel.
Yes, I don't think you're presenting your screen.
Oh, I'm not presenting us. So sorry about that. Let me present. Yeah, I'm presenting this my screen. So this is what I was talking about. I think yesterday we looked at how you calculate channel capacity uh, of a binary symmetric channel, and basically what we are looking at is the channel capacity per symbol. So to find out the channel capacity, you need to multiply that channel capacity per symbol with the symbol rate. And so I was just saying that the channel capacity of binary symmetric channel, it can be shown to be this, and this will form a part of your the next assignment. Not now. When I give you assignment, so you can still investigate now. It's covered very well in uh, the textbooks, but actually from the theory of what we have covered, you can be able to actually establish that the channel capacity per, per symbol, which is the maximum of mutual information, is given by this. And you can see the main thing is actually once you get this, the next thing is to show that the output entropy is equal to 1 when you have the maximum channel capacity. Yeah, yeah, because you can see what this is the output entropy or marginal entropy is equal to 1. This everything else remain the same. So what you are saying is when you maximize the maximum CS is obtained when this entropy, output entropy, is equal to 1. So before we go to coding for discrete sources, I want to look at uh, two solved examples, uh, which I have here. I think this is uh, the examples I want us to look at to help us more understand the concepts. Just 1 second. So in this case, you are given the case of a binary binary. Okay, once we see binary, it means it's a discrete. A binary memory source X with the symbols X1 and X2, and you are to show that the entropy or the source entropy is maximum when X1 and X2 are equiprobable. What you are saying is when X1 is the probability of X1, Px1 is 0.5, and so is Px2. The solution, and this is how we approach it, let Px1, the probability of X1, be equal to alpha, and the probability of X2 be 1 minus alpha, because the probability has to add to 1. Actually, what you're trying to show is that the probability is 0.5. So the entropy, yeah, so the entropy is given by this. We are just simply expanding the formula for entropy, the summation. So for the two symbols, this is what you're going to get. That is px, this px log 2 or px minus px log 2 of 1 or p, I mean px. Yeah, I think we are quite familiar with this. This negative is simply coming from 1 over alpha. So that becomes, if you take it to be alpha, then that becomes minus alpha. Yeah, and the same with this. I hope this is clear, because we are simply adding the two. Yeah, this is just a summation. So let me put my phone in silent. So this is just from the formula that where are we? The formula of entropy, that is where I, we just put I, whatever it is, and then pi log 2 1 over pi. Yeah, oh, actually it's not pi, it's p, we just call it pxi. Yeah, epsilon, which is varying. Yeah, pxi. So this goes from 1 to whatever level it is. So this is what we are saying for two of them. Of course, this is what you're going to get. You're adding the two, but since they have a minus sign, it's minus. So hx is equal to that. Now, what we are trying to get is what maximizes h of x, and we are saying what we can do is we can differentiate h of x, because for maximum value of hx, d by dx of hx is equal to 0. The maximum is when the gradient is 0. I think that we are familiar. We know that the gradient at this point is 0. The gradient is positive, 0, negative. Yeah. Of course, that can also happen with a minimum. Yeah. But for us now, we are interested in the maximum. So for maximum value, this d by dx of h of x is equal to 0. So what we need is to get this to be 0. And what we are going to do, we are going to use two formulas, which I am differentiation, where the d by dx, I think we all know it, I'll reproduce it here. D by dx of uv is equal to u dv by dx. I think we all know this, plus v du by dx. That's what we are going to apply. So applying that, and then we are going to apply this other formula here. Uh, the d by dx over log. We say b by dx of log dx is 1 over ln b times x. Well, this is a natural logarithm. Yeah. So somehow the ln would have disappear from somewhere. It will cancel out somewhere. So we can use these two formulas, the product rule. I mean, this formula and this product rule that just outlined here. So dh, in our case here, we are integrating with respect to alpha. So d by hx by d alpha is given by, in this case, we are going to apply for both cases, both for this one. This is u and this is v, and this is u and this is v. We are going to apply for both cases. The product rule for both cases, for this and also for this. And that is going to give us all those terms. The first one is, for this case, minus alpha d by dx log 2 alpha. This one plus minus 1, which is that is d by, because for this one you know d by dx of minus alpha is minus 1 log 2 alpha. Yeah. So here we're just doing this. Yeah. So we get that. The second case, minus 1 minus alpha d by d alpha log 2 1 minus alpha, plus, again, we know this one, when you do d by dx of this one, you get minus 1 log 2 1 minus alpha. Yeah. So I hope nobody has a problem with this. If you have a problem, it's good you ask, I can clarify. So you get that, then, and we know that is supposed to be equal to 0. Yeah. So what we end up getting, is now applying this, the logs. You want to finish the logs? Yeah. going to remove this, some of these. Uh, we want to get rid of this. The d by dx is d alpha, sorry. This is what we're going to trying to get rid of, and we are saying that dx of x is x in the numerator. Actually, it's not x, it's the 1 of x. Yeah. Or that x is supposed to be there. Yeah. So that is where we are getting this. This becomes minus alpha, and then the d by dx becomes this d by dx of alpha. This one, the earlier d by dx of log 2 alpha. This first one here becomes this, and the second one here, this one becomes this. Yeah. So I hope we are following. So this becomes that, and this becomes that one here. I hope you're able to see. I think I now send you this document. These examples, I'll send it to you. Nonetheless, I hope you are still able to follow. Uh, so you end up getting this, yeah, because these two, there's something here that is going to, yes, you end up getting this 1 over ln2, because this cancels out. So you get the 1 over the natural logarithm of 2 minus log 2 alpha, and then you have minus 1 over natural logarithm of 2 plus log 2 1 minus alpha. So this cancel out, and you end up having minus log 2 alpha plus log 1 minus alpha is equal to 0. So this is equal to 0. So we are saying if you are adding two logarithms, that should be the logarithm of dividing the 1 minus alpha by alpha, because so same as is the same as this divided by alpha. Yeah. So that gives us 0, and therefore that to be 0, it means this is equal to 1. Yeah. This is equal to 1, and therefore 2 alpha is equal to 1, and alpha is equal to a half. And you can see that the maximum entropy, put this as what it is, that's what we are trying to look. The maximum value of entropy, of course, will be when you're replacing alpha with a half. So that becomes that. With this simply a half log 2 a half, yeah, uh, which becomes 1 bit per symbol. Yeah, this 2 is because it is 1 over a half, 1 over pi. Yeah, so it becomes 2. And that gives us 1 bit per symbol. It's just something which one didn't understand, or a step which you didn't understand. Yeah, so here the problem was just to show that for a DMS, a binary source with only 2 symbols. So that's what a binary source is. There's only 2 symbols. you can show that the maximum entropy is achieved when the two symbols are equiprobable. Yeah. When they have the same chance of being generated. Always remember, whenever we talk of entropy, we associate entropy with a source. When we talk of, and therefore we are talking about joint entropy, then that is associated with a channel. Yeah. So if there are no questions, we can do a second example related to this. The second example is consider a binary symmetric channel shown below here. You are given two symbols, x1 and x2. You are not being given the probabilities. I think for this case, you're given probabilities here. Yeah, you are given px1 and px2, and then you are told to find the channel matrix. Always remember, channel matrix is this is a channel matrix, the transition matrix. Yeah, a matrix of transitional probabilities. That's what we call it. So it is P of y1 given x1, P of y2 given x1, P of y1 given x2, and P of y2 given x2. And of course, we know P of y1 given x1 is 0.9. P of y1 given x2 is 0.2. Yeah. So at least we know this one. Y1, so this is point y1 given x1. So this is 0.9. This one. This one, y1 given x2. Y1 given x2 is 0.2. Yeah. And then the next one is P y2 given x1. Y2 given x1 is this one, is 0.1. So that is 0.1, where is 0.1? 0.1. And of course, P2 given P y2 given x2 is this one. Yeah. So the next, that's the first part. The first part is answered. The second part B, finds py1 and py2 when px1 and px2 is equal to 0.5. x1 and x2 are equiprobable. They are 0.5. They may not always be 0.5, but in this case, you're given as 0.5. So that one, the formula is this one here, just px multiplied by pyx, which is 0.5, 0.5 multiplied by this, and you're going to get, so this is 0.45 plus 0.10, that's 0.55, and this other one is 0.05 times 0.4, so it's 0.45. So I think that part is straightforward again. But if I move too fast, please ask. Yeah. As I say very often, when we go online, it places more responsibility on you, especially if you're not understanding than a physical class where I become a mind reader. Now here I'm not even seeing your images. You can see mine. So the best you can do is if you don't understand, kindly ask. Yeah. So then the last question, find the joint probability. Px1, Py2, Px1, y2, and Px2, y1. So what you need is the this um, Pxy, yeah, and this one is given by this formula. You're going to use Pxd. Pxd means the diagonal matrix. Yeah, this is Px, Px. This is Px. You see, and this is Pxd. You have to convert it into a matrix. Yeah, which you call Pxd. Yeah, you have two symbols, so you have to create, because this matrix has to be able to be the same size as this matrix, so that you can produce a 2 by 2 matrix. Yeah, so this needs to be a 2 by 2, like this one, so that you can produce a 2 by 2 matrix. So we use this Pxd. We make this diagonal and multiply the 2, and this is what we are going to get. And this is Px1, y1. Always remember the rows are the x's, so this will be x1 and this will be x2, and the columns are the y's, so this will be y1, this will be y2. Yeah, always remember that's what you don't have any confusion. Yeah, yeah, as straightforward as it looks, I see normally a lot of confusion. Sometimes somebody interchanging, and therefore you end up getting the answer wrong if it's in a test situation. Yeah. So when you multiply out, I think we are all familiar with multiplication. So this term will be 0.5 plus 0 is 0.45. This term will be 0.05 plus 0, 0 times 0.8. So you get that is 0.05. This term will simply be uh, 0.1 plus 0.4. Plus 0.4. No, sorry. This is 0. His 0.1 is 0. 0 plus 0.4. Oh, that will give us this one. The last one. Sorry, forgive me for that. It is this plus this. So that's how we get 0.1. Then this one is that plus that. Yeah, I think we are familiar with that. And again, answering questions is very important, the way you asked. Because sometimes you can find somebody is asked that and he just produces this matrix and the ends there. So you still have not asked the questions. You are being asked specifically for Px1, y2. So that is 0.05. Don't let me deduce from this. You're supposed to reduce yourself and give the answers correctly. So those are the uh, answers. We want Px1, y2. Px1, y2 is this one here. Y2 is here. The x1 will be on this row. So px1y2 and px2y1. So we want these two. That is the answer. Did everybody understand how we did example 1? Did everybody understand how we did example 2? I try to look for examples that will try to look at different aspects of what we have covered. Yeah. So let's go to the last example. This is an example uh, which is not a bit straightforward. You see, sometimes you'll be given a straightforward where you're given x1 and x2 is equal to this, and then find out what the probability of x1 and probability of x2 is this, and then find out. Sometimes you'll be given a problem, just explain so that you find out what is x1 and what is x2, or by your own. So this is actually such as an example. You're given a telegraph source having two symbols, a dot and a dash. Basically, the original Morse code. Yeah. The dot duration is 0.2 seconds. The dash duration is 3 times the dot duration. The probability of dot is twice of the dash, and the time between symbols is 0.2 seconds. Calculate the information rate of the telegraph. This is how you approach it. P dot is 2p dash, because you have been told the probability of the dot is that twice of the dash. Yeah, and they are saying p dot plus p dash, which is the same as 3p dash, because we know p dot is 2p dash, is 3p dash must be equal to 1. That is the total probability is equal to 1. P dash is 1 over 3, and therefore P dot is 2 over 3. So let's find out the entropy. The entropy is simply minus P dot. That's the probability of the dot multiplied by the logarithm of P dot minus, yeah, and this minus P dash log 2P dash, and that comes that. This one you can work out, and therefore this becomes 0.918 bits per symbol. So T dot is 0.2 seconds, T dash. So there we have gotten the entropy, but I think we are trying to get the information rate. That was our question now. Ours was information rate. So P dot is 0.2 and this 0.6. So the average symbol time, the average time for the symbol is this. So we get the symbol rate. Yeah. So the information rate is simply, average information rate is simply R times the entropy. Yeah. So in this case, you can see we don't have output entropy and input entropy. But so there is no transfer information, but still you can talk about the average information rate being produced by that source. Yeah. We are not talking about information transfer. We are not talking about mutual information. We are talking about the information read from the source. Yeah. So that the information rate is we multiply the symbol rate R multiplied by the marginal entropy, which is the source entropy. Yeah, so this is a different scenario. We are not talking about mutual information because I said mutual information is associated with a channel, but information rate can be associated with a source. Mm. I think with that, then maybe we can go to one of the most important uses of applications of information theory, and that is coding for discrete sources. What we mean here is you told me, and I think I saw in your syllabus that you did coding for analog sources. For example, when for example voice, you want to change your voice um, from analog to digital. And so you have to go through a process. And Soba, Yusuf, Mohammed, just tell us for analog source what you have to do to be able to use a digital transmission system. The steps you have to follow. Just give me the first step. Somebody will give me a second step. Soba Yusuf. Are you there, Yusuf? Okay, Yusuf is not available. Kimaiga Rebecca.
We should use an ADC first.
You are there. Oh, thank you. Yes, you can use an ADC. Okay, that will give you. Okay, just give me the processes. Okay, what basically what an ADC does? It does it in a number of processes. So what does it do first?
I think it samples first, and then
Yes.
it quantizes,
Yeah.
and then codes.
And then codes. Very good. Yeah, I think Yusuf has answered us. So you quantize, I mean, you sample the signal, first of all, to make it discrete in time, and then you have to make it also discrete in amplitude. That's why you quantize, because remember the distribution of those values you get is continuous. It can be any value. Yeah, it's continuous. It can be any value. So you'd have also to discretize it in amplitude. So you do that through quantization, and of course also you create a finite amplitude levels, because at the end of the day you want to represent those levels as codes. That is the whole idea. You want to represent that as codes. So that is for an analog source. Yeah, but one of the other possible sources is a keyboard. And why the keyboard is very critical for us is because uh, for a long time we used to have just dumb terminals sending key, uh, where we just hit. You see, nowadays we might have a lot of processing inside the PC, but you can imagine in the days of the mainframes, the the terminals were dumb. So what you actually send when you strike a key is actually the codes representing that key. You know, so that is the case we are looking at, where is a discrete source, because a keyboard is a discrete source. It's not a digital source, but it's a discrete source. Yeah. So we are saying in that case, uh, one of the most straightforward uh, encoding for this kind of a source is what we call the fixed length coding. Fixed length coding is like ASCII or FCDIC. Those are fixed length encoding schemes. Fixed, that should be something like ASCII, FCDIC. I think it's written like that. Yeah. There is a UTF. So all those are fixed length encoding schemes. But information theory tells us that we don't have to do this, because when you do this, we use a lot of symbols. So if you have a sentence, I don't know which is the best sentence to use. I'll just use my normal example, the one I love using most. Okay, maybe it really I can change. No. Let me use the one I know, because the one I know what it will give me. My abracadabra example, my the magic abracadabra. Abracadabra. I think I talked about this during the introduction, I hope. So in the abracadabra example, you have this word. This word you can encode it as ASCII. Let's assume we are using the 7-bit ASCII, the original ASCII. I think there's ASCII 2. So ASCII is 7-bit. So in this case, you have got abracadabra, you have got 11 characters, 11 symbols. So if you are to encode this using ASCII, you would use 77 bits. Yeah. And if you are writing this word many times or similar words many times, of course, it means for each of this word, you have to send 77 bits. Yeah. And what we are saying is we don't have to do it. We can actually encode the symbols as per the information as their information content. Yeah. As the information content. Remember we said ij is equal to log 2 pj. Oh, 1 over pj, sorry. Or okay, I can just say minus log 2 pj, yeah. Ah, yeah, or maybe I can say ixj. So I'm going to talk about x symbols, and j just a. Okay, maybe it's better to put the x. That makes more sense because j, we use j when you have more than one symbol. So it is actually just ix is equal to log 2px, the probability of x. Yeah, I think that is the best way to put it. When you put ixj, it means the j symbol. Yeah, so that is what we are saying. You can encode such that the length depends on the information content of that symbol. Yeah. But just like you remember with the analog signal, you say that when you sample, to be able to reproduce your signal at the receiver, because that's the whole idea of communication, is you're trying to transmit your signal, and in digital communication we are trying to transmit your signal, which represents your data, your bits. And you want to be able to recover that information at the receiver. That's the fundamental reason for communicating, or objective of communicating. You want to be able to produce your data as accurately as possible at the receiver. So in the case of the analog case, we see that you have to be guided by the Nyquist criterion, where the sampling rate has to be twice. Actually, I should be asking you that because I find also Samuel. What does the Nyquist criterion state? Nyquist has many criterions. The sampling criterion, Nyquist sampling criterion.
Yeah, the sampling frequency should be at least twice the maximum frequency.
Maximum frequency of what?
I'd say of the signal being sampled.
Yeah, that is true. Because the signal is a composite signal, it has got many frequency components. So normally it's good to say the maximum, I mean the frequency of the uh, highest, twice the highest frequency of the highest component, or rather among the components, the highest. That's why we say if it is for audio, the highest will be around 4 kilohertz. But of course, the signal will consist of many frequency components. Yeah. Yeah. So that is the criteria we use for the analog keys. Now for these symbols, what is important is this source coding theorem, which says that a discrete source with entropy H can be encoded with arbitrarily small error probability at any rate L bits per source output, as long as L is greater than H. Actually, this L is the average bits per source. Yeah, because there will be because what we are saying is we are not coding at one fixed length. We are going to code as per their information content, but we are saying the average length. We will actually this average length must be greater than the average information content. So that's what this is. Yeah. So where H is entropy rate, you see, you're calling it rate because it's an average, and L is the average code word length, and is given by this. What you are saying, some may have length 1, some may have length 2, some may have length 4, where the length means the number of bits you have encoded that in. That's what length means, and we are saying the average length is given by this formula. Yeah. So long as L is greater than H, then you can do that. Or rather, what we are saying is the entropy is the limit of compression, because you are saying you can keep on compressing, is the lowest rate which you can compress at, because we are assuming if you use this, if you encode as per the information rate, you achieve compression. Yeah. In this case, we are saying you are going to use fewer bits than you would use if you use other methods like fixed length encoding. Yeah, not even another method, because it is either fixed length or not fixed length. Then you so when we talk about compression, we are comparing with fixed length encoding. Yeah, because it can be a bit tricky when we use the word compression, because we understand compression to mean removing redundant information. Here we are talking about avoiding redundant information. Yeah, because you are saying if you use ASCII, you will actually be sending redundant information, because you had another option of using entropy and therefore use less information. Yeah. So instead of trying to get rid of redundancy, we are actually avoiding redundancy, so to speak. Yeah. So the average code word length can be calculated by this. And normally this one is very easy to see with the calculations. Sometimes when it's explained, it may not be clear. Well, with my abracadabra, I didn't tell you the next step. Of course, we said abracadabra would use 77 bits, abracadabra. But we are saying if, yeah, if you represented this A, because A is appearing 5 times. If you represented A with different bits, with a different length, from let's say D, D appears only once, and the C appears only once, with different length, you could probably say, and it makes sense. Because suppose you decided to use, let's say, 1 bit for C, then C will only contribute 1 bit. If you use 1 bit, C will contribute only 1 bit, representing only one symbol. But A, if you use 1 bit for A, it means for 5 symbols, you're using 5 bits. If you use 2 bits for A, that will be 10 bits. But if you use 2 bits for C, it's only 2 bits. If you use 3 bits for A, it means 15 bits. So A alone is contributing 15 bits. But suppose you use that for C, that will only have 3 bits. Yeah? So it makes sense that if I'm to present this one, I would I would represent this one with a fewer number of bits. So because this one increases much more than this one, I would use the long number of bits with this one. Yeah, because we are going to see that, for example, if you suppose you decide to use this, let's just think about this and forget other A, B, C, D, R. I think those are the ones. If we represented this as 1 bit, 0, we represent this as 1 bit, 1. We are going to see that once you do some of these things, you can't do this, because once you do this, then you can't represent these others, and we are going to see why. Yeah, but let's just suppose you didn't even know about those other conditions. You use 0, 1. Then the next one has to be represented by 2 bits, because the two conditions of this and this is used up. So the next one, we can use either 0, 0, and maybe we use this 0, 1, and this 1, 0. And you can see in this case, actually, let me remove all these. So that we can do some math here. So we have found what is happening. Oh. Sometimes my computer acts up. Okay. We have seen that for abracadabra, we have seen A is equal to 5. Abracadabra. B is equal to 2. Cadabra, abracadabra. Oh, C, abracadabra. C is equal to 1. Is equal to 1. And this is equal to 2. I think that's it. That's how you get the 11. So suppose we decide we use this as 0 and use this as 1, use this as 0, 0. As we go on, we can't use this. We'll be guided by something. But let's suppose we don't know those other rules that are going to guide us. Now, if you are to do your abracadabra, there are 5. So this will be 5 bits. The contribution of this will be 5 bits. It's not 0 times 1. This is the length 1. So this will be 5 bits. This will be 2 bits. 5 plus 2 plus this is 1, so it is 2 bits, because this length 2 times 1. The same here, 2 bits, and this is 2 times 2, and so this is plus 4 bits. So the total number of bits you can use is 15. Yeah, but of course this is less than ASCII. Of course, you can't compare with ASCII because ASCII is meant for 128. Is meant to cover 128. It has an alphabet of 128. Here we are saying our alphabet is only this 5. Yeah, that's why we are able to use this. With more alphabets, you can't do more than this. Now, you can't do this with more alphabets. You can use another one alphabet, 10. So maybe you have a 6th alphabet. If you have an alphabet with 6 symbols, maybe you could do that. Yeah. But suppose we decided to use 1, 1 for this and 0, 1 for this and 1, 0 for this, and we use 0, 1. Let's see what you can get. This will be 2 times 5. That will be 10. Plus this 2 times 2. Because there are 2 bits. The length is 2, and there are 2 of them. That means plus 4. Plus this is 1. So that is 1. And this is 1 plus 1. And this is 2. 2 times 2, 4. So in this case, we are going to use 20 bits. You see, when we present, I guess it's common sense, but it's intuitive. If we represent the longer one, I mean the one that occurs many times, and occurring many times means is the most probable. Yeah, with a longer length, you get more bits. If you use the shorter length, you get less bits. So what you're going to look at today is algorithms that not only end up representing the more frequent ones with shorter bits, but also it ensures that your code has got a very important property which we call prefix free. Now, this one, I think for our case, I'll say from the beginning, so that we don't have any any misunderstanding, because textbooks refer to it differently. Now, if you have um, a word, whether it is letters or is a word made of bits, it will have a prefix and a suffix. You can divide it somewhere. Yeah. And if it's 101, you can have one as the prefix and 01 as the suffix. Or you can have 01 as the prefix and 1 as the suffix. Just two parts. The first part will be the prefix, the second part will be the suffix. And what we say is our code has to be prefix free. Yeah. Prefix free would mean you can't do this, because the moment you use 0, then 00, this A becomes a prefix of C, because this 0, this is A. Yeah. So it becomes a prefix of C. Yeah. So that already makes it not a prefix free code. And it also becomes a prefix of D. Yeah. And of course, B becomes a prefix of R. And of course, it means this is not uniquely decodable. Because once you send this to the receiver, because you are doing this for transmission, remember all the time, whatever you're trying to do, you're trying to do it to help you recover your signal at the receiver. When you remember that, you never go wrong within a process in communication. You are doing it. Why are we doing it? Because we want to be able to recover at the receiver. So in this scenario, you can't be able to recover at the receiver, because the moment the receiver receives this, it doesn't know whether it is C or it is two A's, because this can be AA. So the code is not uniquely decodable. So you can't have that, you can't transmit that. Yeah. Now, why I was mentioning this prefix is because for us, I want to use the word prefix free to mean a code whereby none of the symbols is a prefix of the other one. Yeah. And I say that because some textbooks now use the word prefix to mean the one which is prefix free. So they'll say this is a prefix code. A prefix code meaning is a prefix free code. But for our case, I want us to stick to a prefix free code instead of the prefix. Yeah. So in the, information theory, sometimes prefix just means prefix free, which is odd. Yeah. So we are going to look at different algorithms. We are only going to look at two that are able to give us prefix free code that makes them decodable, uniquely decodable. And another one, okay, there's also another one, I think it's the same, it's called instantaneous code. A code is instantaneous because you can be able to um, decode a symbol without having to look at the next symbol. Yeah. Once you see that symbol, once you see the code, you can be able to decode it without looking at the next one. Yeah. When that is possible, we say it's instantaneous. So instantaneous is sometimes used to also mean prefix or prefix free, depending on the order of that material. But for us, let's stick to prefix free code as prefix free code, not as prefix. just use of terminology. Yeah. Okay. So I think I've talked about this. Um, of course, this is a definition of a DMS, a discrete memory resource, is the one that has property that its output is a certain time does not depend on its output at an earlier time. Because we are talking about a source. So here we are not talking about inputs. So it's easy to differentiate the DMC and the DMS because a source only has outputs, what it's producing. Because sometimes I see confusion when you ask somebody what's a DMS, they say the property that is output does not depend on the input. No, there is no input. This is a source, and therefore it has only output. So what it means is output at a certain time does not depend on the output at earlier time. But we say again, most of our alphabet or most of our languages, if you are typing a keyboard in English, you know some of your it may not qualify to be a DMS because we know U is likely to appear if the last one was a Q. Yeah, yeah. It's more likely to appear if the last one was if the last one output was a Q than if it was A. Because A maybe you can only come if the word is auxiliary. Yeah. But when you have a Q, almost it means it's probably what follows being a Q, a U, it's almost 100%. Yeah, I think it's 100%. I don't know that other Q's can be followed by something else. It's just U. Yeah, in English. Yeah, if you see it followed by something else, probably the source is not the original is not English. Yeah. So we come to entropy. So it is possible to represent the bits with less number of, I mean the symbols with less number of bits without losing any information, so long as the average length is greater than the entropy. The code must be prefix free and uniquely decodable. Of course, unique decodability is enabled by being prefix free. Yeah. Nonetheless, we still use the two words, but unique decodability means it has to be prefix free. So entropy, and the beauty about entropy encoding is that it is lossless. You don't lose any information with entropy encoding, unlike these other lossless techniques. Uh, well, we are saying is lossless as a compression technique, yeah, because you are encoding, but you are attaining compression. So it is better, and you can see why we use it, why we do this entropy encoding, because you are trying to achieve compression with the characters. Yeah. If you change anything, you see normally with the compression what you are doing. For example, just what Junior, can you tell us just one lossy compression technique? Give us just one lossy compression technique. Matasio. Rebecca Kimaiga, one lossy compression technique. Okay, anybody? Probably something you use. I'm sure you use it. Or it is. Yeah, I think we all use it. MP3 is a lossy compression technique. MP4, all those JPEG, MPEG. But they work with images. And the video. Of course, videos are just images. Moving at a certain frame rate. Actually, videos are just frames of images. Yeah. So those are lossy compression techniques. And of course, it's easy to do those with the images, because what we are saying is we can remove certain things from that image, and the image will still be depicting what is it's supposed to be depicted. It will not be the same clarity. It will not be the original, but it will be good enough. That's why we say that is a lossy compression technique, but you are still able to see your message. If it is music, it is compressed into MP3, and compressed I think should be a wave file that will be uncompressed. Yeah, but um, but you can still be able to. The music is still good to you, good enough to you. It's distorted, but you don't know, or it sounds okay. So, in for the purposes of saving your storage, you're okay with it, but it is lossy. So of course you can't use that with symbols, because the moment with the symbols, the moment you remove something, the meaning changes. So if for example you're trying to say shut the door with a train of pulses, or rather with a sequence of beats, then probably that might do the opposite. Yeah. If you try to compress, if you try to remove some bits, it will change the meaning. But it's easy with images to do lossy compression technique. But this one gives us an opportunity with the characters to um, achieve compression without any loss. Of course, there are other methods which are lossless, like run length encoding. I think the one I think I was trying to mention, I don't know whether I mentioned run length, whereby you can just yeah, I think somebody even asked me a question about it, where you can be able to represent continuous zeros with with that particular symbol or bit, and then saying how many times it appears after that. Yeah. So here we are. So we are going to have a look at. We are going to use Huffman coding algorithm, and then we are also going to look at Shannon panel encoding algorithm. So here we have a memory source that generates 5 symbols with these probabilities. It means maybe you have done an experiment, you have written a passage, and you find that with that passage, and that passage you're only using these 5 symbols. We know it's not practical. You need vowels, more vowels, you need other consonants, but you're only using these 5 symbols. And you have found that this is a probability. Maybe you wrote 1,000 a passage with 1,000 words, 1,000 characters, 1,000 symbols, and A appeared 270 times. B appeared 250 times. C appeared 220 times. D appeared 170 times, and D appeared 90 times. That will be that probability, yeah? So you are supposed to generate symbols, generate codes for these symbols using Huffman encoding. The solution, and again, it's good to know these steps, because sometimes you find, especially in an exam situation, you are told to create a Huffman tree. And what happens? You end up creating another tree. And that tree you have created because you have made a mistake in the process. So you'll be wrong, because the assumption of the person marking the exam is that you got the wrong tree because you didn't use the correct algorithm. So if you are asked such a thing, it's always good, first of all, to enumerate the algorithm you are using. It's good to write down the algorithm you are using. So even if you get it wrong, even if your tree looks different from what is expected, it is clear that that was a mistake and not knowing. So that's my advice. Even if you are just told to do the tree and you are not, of course, in some cases you are told show your steps or explain your steps. In that case, you'll explain this. But even if you are not, it's always good to write this. Just in case your answer is wrong, you create the wrong tree. You are going to see how a tree looks like. So these are the Huffman encoding steps, and of course, what you end up getting is something like this, which we call the Huffman tree. Now, we are going to see in some textbooks that you don't have this kind of tree, top-down tree. They would have a horizontal kind of tree, but I don't like the horizontal tree because it doesn't really create that top-down or bottom-up approach, which is actually we are going to see, yeah, when you use this tree. So the algorithm is arrange symbols in descending order of probabilities. You see, like here you are given, you have already given them in descending order, so it is easy. You are starting from here. Sometimes they may not be in descending order of probability, so you have to put them in descending order of probability. Merge the least two probable symbols or subgroups into one subgroup. So in this case, our two most probable symbols are these. So we are going to start by merging these two. And then you are told assign 0 and 1 to the higher and less probable branches. So of course, since they're in descending order, it means you assign 0 to this one and 1 to the less probable. Higher probable are 0 and less. So if you have this is how your tree looks like. So the two are these ones you have merged into one node. So this one will be 0 and this will be 1. That's what it means. The more, because the more probable is on the left. Yeah? And the less probable is on the right. So the more probable gets a 0, the less probable gets a 1. If there is more than one symbol or subgroup left, return to step 2. Like here, of course, these are more than 2. So you go back to step 2 because what has happened is the moment you merge these two, I think that's the part we did not see that you have to organize this now because this is 0.26. So this now comes here. Yeah. Because what you end up getting now is 0.27, 0.26, 0.25, 0.22. So the next margin will be these two. Yeah. Because now you have already merged these two. So in the next step, what you have is 0.27, 0.26. Combining these two, 0.25 and 0.22. So the next step, you are going to merge these two. And when you match these two, of course, they will come here. So now you have 0.47, 0.27, and 0.26. Yeah. So you keep on doing that until you have only two symbols, which 0.47, sorry. Which of course they would add up to 1. They should add up to 1. Yeah. No code word forms a prefix for any other code word, so they can be decoded unambiguously. We are saying once you use this algorithm, what you get is uniquely decodable because, or rather, unambiguously decodable because it no code word forms a prefix of another code word. And all the time, whenever you hear a code word, is what you create after you apply some coding algorithm, whether it is in source coding, which we are doing now, or it is coding for error control, which we are going to do later. Whatever it is, the code word is what you produce after you encode. That's the general word for a code word. So let's see now what happens in this example. We have started with the 2. Of course, sometimes if you are just being on one table, you may end up not even having the correct order. But that does not change it from being uniquely decodable. Because sometimes if you are just doing in one table, the probability is you don't want to keep on moving this from this side to this side. What I mean is, for example, let's see whether we actually got the correct order. Like you see this DE, you can see it has come here, but initially, of course, it was somewhere here. Yeah, DE you had combined, and of course, what will happen is you'll have to move this to here. You can see now it has moved. DE is here. This is DE. This is 0.27. So initially you had 0.09, 0.17, I think that's what it was. So this became 0.27. You see, there was an organization, a reorganization. This became 0.206, sorry, and this is 0.27, and this is 0.25, 0.22, and this is 0.47. Is it 47? And this is 0.53. You see, what I'm saying is when you're forming the tree, you keep on moving this because at one time this was here. Yeah. So you have to keep on organizing this, but eventually this is the tree you get. That's why sometimes I prefer this method because it explains that this is a bottom-up approach because you are starting from the bottom, you are going up. And so, I did not give the steps, but the steps, of course, the first one was combining these two. And when you combine that two, then the next one will be to organize that these two are in the position they're supposed to be. So there will be that, and then there will be these two, yeah. And then you combine the two, and once you have this, now these are the lowest. So ordinarily you have brought this one here, yeah. This one should have come here, so this is bigger. But it will come automatically once you do step by step. You'd get this diagram. I mean, this what we call the Hammond tree. This is Hammond tree, and what you do eventually is you will be asked to create the code, or you may be asked to create the Hammond tree. Of course, if you do this, you already have the Hammond tree. But if you ask to give the code, then it's good that you enumerate it like this. You put your code words like this, which is whenever you have this, you have two leaves to a node. The left leaf, well, these are not leaves; they are branches. Leaves are these are the final one. So the left branch takes a 0 and the right branch takes a 1. So that is 0, 1, 0, 1, 0, 1, 0, 1. Now the code becomes 0, 0, and you always start from the bottom. 0, 0, 0, 1, 0. Actually, it will not even change anything. Actually, will it? No, it will not. I'm trying to see whether it will change. It will change. Actually, you can start from the top. Like here, we have started from the top. 0, 0. B is 1, 0. C is 1, 1. D is 0, 1, 0. How you get from the root to the leaf is 0, 1, 0. And this is 0, 1, 1. And you can see what we have produced is actually prefix free. This prefix free because this is 0, 0. So it means there is no other code that starts with the 0, 0. There's another code which is a prefix, which this makes a prefix of it. Yeah. So the next is 1, 0. It means there is no other code which is 1, 0. Starts with 1, 0, and you can see that is okay. 1, 1. It means there is no other code starting with 1, 1. So this 0, 1, 0, this 0, 1, 1. They can share the prefix, but that prefix is not one of the codes. So you can see why you cannot use 0, 0, 1, 0, 1, 1, and 0, 1. Because the moment you have 0, 1, then you cannot have anything else because now you have already utilize that. So that is uh, what you'd get from the Huffman tree. That will be the Huffman tree, Huffman code, or rather the code you get if you encode this using the Huffman algorithm. And actually, this is used a lot with our keyboards. Most of our keyboards actually use the Huffman. You can actually go and buy this Huffman IC. Uh, it will be part of your keyboard. So they are available. Yeah. If you want to use character encoding for whatever reason, maybe for a project, you can do it using a Huffman uh, code generator. So, any questions? I was thinking we stop there so that the next time we are going to look at the code efficiency, how you find out the code efficiency. We also find out about something we have not talked about. Crafts, I think I didn't write about it. Crafts, Macmillan inequality, which is a necessary condition. Yeah, sufficient and necessary condition for a code to be uniquely decodable. Yeah. So we'll stop there. Is there any question? Does anybody have a question? Yeah. Maybe I can ask. Suppose we got this code. Suppose our code was if this is what we got on the Mkapa Titus, is this a prefix free code on there?
No.
Why?
Because we have 01 and also 010 on the third.
Ah, thank you. Because we have this and this. That's already removes it. Of course, also this and this. And even this. So this is not uniquely decodable because it is not prefix free. So let's do what we normally do. Let's just our um, let's post our registration with our proof of attendance.
Excuse me, sir.
Yes.
Did you say that trees, the trees can be different for other people?
No. It may be, you can use a different method there, but what I was thinking, sometimes it can be different. For example, if you are doing on one page and you don't want to keep on moving this from left to right, you will find that you get a different tree, but still it works. I've seen it works. The one which does not give you a different tree is when you organize them. Even this should not be a different tree. So long as every time you're supposed to move, you move it to the correct position. You see what I mean? Once you create this, if you're doing it on one page, you're going to avoid having to move this entire to the left or right. So it will still give you a correct tree. It will still work. That's my experience. But ideally, you're supposed to when you add something and it becomes more than the other ones, how you move it to its actual position. But I've seen even if you don't, that's changing anything. But the other method, which is actually the one recommended in the textbook I gave you, it's where you organize them such that so you just keep on, where you organize them from the highest to the lowest. Then when it becomes smaller, you take it down, and the ones which you have added, if you add these two, they become more. Take them up. That is the method in the textbook. That's why I'm saying I like this method. Uh, is that it clearly demonstrates on the put of your microphone, in the top of your microphone. Yeah, thank you. Yeah, this method gives us this interpretation that this is a, a bottom-up approach, because the other common, this is the most common, but the other common one is what you are going to call the Shannon funnel. Shannon funnel is a top-down approach. So this tree demonstrates that, yeah. And I find it's easier to think of a tree as having branches going down, other than this one. This is still a tree, but it's a kind of a tree which is lying down there. So this is normally easier when you are doing it, because this one, yeah, if you show the stages, you end up getting the correct tree. Yeah. Maybe we need to because like now when you're saying this is 0.27, it may start being in this position, but when you draw it, it will come here. But what I'm saying, sometimes you might find somebody has a tree whereby all this is on the right. It's not the correct tree, but the code you get is still uniquely decodable. Yeah, that's what I was trying to say. Yeah, so you might have all this, the whole tree on the right and this on the left, but it doesn't change the unique decodability. But it's not the correct tree. Yeah, so you have to be careful when you're doing that tree, so that you get the correct tree. You have to keep on moving this because the first time you arrange, you're going to find this one is on this side. You arrange again, you find it is smaller, is coming on that, going to the right. But if you have shown the stages, that should not be a problem. Yeah, but again, you can't be penalized if you use the other method of where you organize the probabilities from in descending order, and again, now you keep on moving them again as you combine. You keep on moving them, the positions. Actually, it's a very easy one. Yeah, but also this one is acceptable. And I use this one specifically to explain that the Hammond tree is a bottom-up approach, while the other one we are going to use, the Shannon funnel, is a top-down approach. Yeah, so we'll stop there. Let's meet next Wednesday. Have a good rest of the week.